So now we're going to talk about quantum computing, right? So in the area of optical slash photonic computing, there's a lot of different subcategories that we could use to talk about, quantum computing. And we're going to focus on quantum computing, right? Okay, so quantum computing is the use of quantum mechanical phenomena such as superposition and entanglement to perform computations, right? Computers perform quantum computation are known as quantum computers, right? And they're believed to solve certain computational problems such as integer factorization faster than your average computer, right? Than your average traditional computer, right? So there are several reasons why, building on quantum computing is a good thing, right? And there's a lot of applications that we've developed in that span. Things like quantum cryptography, which is the ability to send or permit the secure transmission of classical information, right? Quantum simulation, right? Which can increase our understanding of how quantum systems work due to the unpredictability of quantum states, right? Quantum supremacy, right? Which is when a quantum computer executes instructions faster than like a regular computer would, right? And the last but not least, that's it. I'm just messaging. But yeah, so despite all these applications, right, that could revolutionize computing, quantum computing is still in its infancy stage, still in its that beginning stage, right, where it could still massive room for improvement, massive room for development and evolution, massive room for progression in the future, right? So, with that being said, quantum computers are so hard to engineer, right? Build and program. It's hard to engineer it. It's hard to make it. It's hard to build it. It's hard to program it. It's just everything with quantum computing is kind of difficult, right? It's not easy. That's not an easy task, right? And as a result, there could be errors when building a quantum computer, right? Such as the noise it can make, the faults and the loss of quantum coherence, which is crucial to their operation, and it kind of falls apart before any program is being able to run on the, computer itself, and that's known as decoherence, right? That whole process of things not being done properly is called decoherence, okay? And another problem is the loss of qubits, which is quantum bits, right? When performing error correction, right? So when a quantum computer reads hundreds, if not millions, if not billions, right, of bits, right? When it's reading it to check to see if there's any errors, it uses the qubits. Right? And it uses qubits so much that by the time you want to actually run the program that you want to run, the qubit amount is too low, and you probably will not be able to do that, right? The amount left for the actual computation or the actual function that you wanted to run on the quantum computer, probably won't work because the amount of qubits is too low, because it consumes a lot at a very quick rate, right? So, right, qubits is an essential part of quantum computers because their building blocks are similar in the way binary bits are the building blocks to a regular computer, right? In a regular system, a bit would have to be in one state or the other. 0, 1, on, off, right? However, quantum mechanics allows the qubit to be in a coherent superposition of both states at the same time, simultaneously, a property which is fundamental to quantum mechanics and quantum computing, right? Quantum entanglement allows multiple states to be acted on simultaneously, unlike classical bits that can only have one value at a time. Entanglement is necessary for quantum computation that can't be done efficiently on a classical computer. Many of the successes of quantum computation and communication make use of this entanglement, right? Okay. So, with that being said, right, in 2019, there was a whole debate on Google over Google claiming the word quantum supremacy, right? Just because they made a supercomputer that was able to solve a problem that was virtually impossible for regular machines to solve, right? And the processor was called Sycamore, which comprised of 54 qubits, and it completed the task in around 200 seconds. And Google claimed that that task that took the supercomputer 200 seconds would have taken a normal computer around 10,000 years to complete, right? So because that happened, because Google did that, they claimed the rights to quantum supremacy. They claimed to have mastered or achieved quantum supremacy, right? But then you have other companies like IBM and stuff like that. IBM, right? They neglected that. They refuted it, and they said no, right? They claimed it would only take a few days for the supercomputer to do this, right? And even then, right, the debate is still ongoing to this day, right? Scientists and computer technicians and stuff like that, right? They're definitely going back and forth. Researchers are definitely going back and forth on the word quantum supremacy and who is really able to achieve it, and if we can even really achieve it. You know, something that could be, you know, realized within the near future. But if without, despite all that, right, quantum computing is still on the up and up. It's still something being looked into to this day. It's still something that can be improved to this day. It's still something that, you know, is very emphasized on, you know, is very focused upon, right? And there's a lot of advantages of quantum computing and a lot of disadvantages, right? Not really a lot of, there's only one real disadvantage, and the disadvantage is monetary wise, money, right? The money, the cost to build it, the cost to make it, the cost to, you know, run all these things is expensive, right? So it's not necessarily out for us regular people, us, you know, regular society yet. But some of the benefits about it is the way it's demonstrated to be able to, you know, break down tough algorithms at such an alarming rate, being able to, you know, factorize large numbers and things like that. It's just the speed and efficiency at which this quantum computer could answer questions or solve algorithms or equations at such a quick rate that regular computers would take a long time to do seems to be one of the benefits, you know, and it's one of the things that make quantum computing really something to look forward to in the future.
So the second subtopic we're doing a more detailed focus on is reversible logic. So reversible logic are circuits, otherwise known as gates, that have one-to-one mapping between the vectors of inputs and outputs, allowing the vector to always be reconstructed from the vector of output states. The inputs and the outputs of reversible logic gates can be uniquely retrievable from each other. The circuit normally operates in a backwards operation, allows reproducing the inputs from the outputs, and consumes zero power. As the basic elements of any logic circuits, logic gates are usually used to create Boolean functions. So as you can see here, there's a list of the different kinds of logic gates. So we have a NOT gate, a C NOT gate, a Toffoli CC NOT gate, and the fourth one. So these are just different types of reversible logic gates. So the logical operations run backwards by cascading a reversible logic gate. These circuits are very attractive for applications where extremely low power consumption or heat dissipation is desirable in areas ranging from communications, optical communication, to nanotechnology. Reversible logic is also found to be very useful in quantum computing, where the quantum evolution is inherently reversible. Launder's principle is the physical principle essentially stating that for a set of executable instructions, there is a minimum energy cost associated. So in theory, no matter how much we improve our technology, there will still be a minimum energy cost of using irreversible logic, which creates waste in the form of heat. The notion of reversible logic is to determine what was the input was from only knowing the output, which could in theory circumvent Launder's principle. So this principle is basically stating that in traditional computing, the waste that is created by irreversible logic is in the form of heat. So when you use reversible logic, you're removing that energy waste that is created. So that's a huge benefit in reversible logic. So in terms of potential implications and uses for the invention of reliable reversible logic going forward, they include eliminating the waste or heat that our technology generates. We could determine input variables or vectors just from knowing output variables or vectors. So this is one of the main properties of reversible logic. And we would have faster computers as no waste will be generated via heat, and that will slow down a system. So something that would need to be achieved for it to be considered reversible is a multiple Boolean function would be considered reversible if the number of outputs is equal to the number of inputs, and any output pattern has a unique preimage. In other words, reversible functions are those that perform permutations of the set of input vectors. So in other words, you'll be able to just get the input from just knowing the output and then going from there. So in terms of what this means for Moore's law, which is the number of transistors in a densely integrated circuit doubles every year. So that's what Moore's law says. So in terms of that, this irreversible logic will lead to the end of Moore's law because after a certain amount of time, there is a minimum amount of energy that irreversible logic will consume. So after that point is reached, we won't be able to have irreversible logic that is fast enough to keep these circuits doubling every year. So eventually, this law is going to slow down unless we get reversible logic in that time. So if we're able to get reversible logic, then that trend can continue, because then we won't have a minimum energy that we need to account for. So in theory, we could keep Moore's law going into the future. And I think humans will, because we have discovered many very, very advanced technological feats. We have achieved them in the past, and I think we'll continue to keep achieving them in the future. So that concludes our video. So I hope everyone enjoyed it, and I hope you learned something from it. Thank you.